Well, hello, everybody. My name's Philip Brown. I've got a really cool problem right here. We've got these circles, large ones inscribed inside of a square. Got a couple of little clues there, and our job is to find the area of the square. I'm going to do this in two different ways. First is kind of straightforward, although I do not think this problem is easy. I think the solution's not obvious, and it's very easy to get confused. We'll dive into some of that. The second method, though, I use a property that I don't think a lot of people know about. I certainly didn't before maybe 3 weeks ago. Now, I also want to know if you try this problem and you come up with a solution that's better than mine, a little bit cleaner. I would love to hear from it. I read all your comments. I really do like them. They help me to be a better mathematician. Sometimes they help me to just make better videos. So I do love hearing your feedback. Let's dive in and talk about a couple details so we are all squared away with what's happening with this situation. AB is got a midpoint at E, and AD has a midpoint at F. This point right here, we're going to call it G. Both of the circles are tangent to that. The large circle is inscribed, and FH, this segment that has a length of 6, is perpendicular to AD. I found this problem on social media, authored by Assel Lisa, which as a palindrome, I'm thinking it might not be a real name. If it is, whoever named that person, they deserve an A star, because if your name's a palindrome, that's pretty cool. All right. Method number one, here we go. So we know that the area of the square is going to be the side length squared. So we're going to say that's AB squared, right? AB is also the same as that distance right there. And from here to the side is the radius. So if we doubled that, 2r is the same as AB, so the area of the square would be 2r quantity squared. Now within that, we also have a smaller circle right here. We're going to call its radius lowercase r, and so we got that situation here. Now let's zoom in on this part right here, and let's clean up the picture. I had a lot of trouble with this one because I kept getting confused on where the endpoints were and what they really meant, and oh man, it got kind of ugly. So let's zoom out. Clean up a little bit right here. So we know that from here to here is 2r. So we're going to say this black line on the top is the same 2r. We've got that point right there. On the left is 6, and on the right is 2 lowercase r. Okay, so that's the same situation, and we know those two things are equal. We can reduce, divide by 2, right? So now we know that 3 plus lowercase r is the same as the radius of the larger circle. All right, let's put that into context and see what that really means. Well, this plus 3 is capital R. So let's go ahead and put the 3 right there. Pretty cool, right? All right, so now we know that that's 3 and that's R. We could put that all back in our picture right there. And when I did this problem myself, I actually did just like I showed you. I was having so much trouble. I was getting super confused. It's not that complicated. There's just too many parts. So when I just redrew it as a number, as a line, like I just showed you, then it was really clear. All right, so now let's talk about something else right here. We have a Y right here. We know that that's perpendicular, right? So we're going to have some right triangles. All right, so we know that this distance from here to here is also r, so r is also equal to 4 plus y. Pretty cool. Since those are both equal to r, they're equal to each other, and we can solve it. So let's go ahead and subtract 4 from both sides. There we go. So y is going to be equal to r minus 1. All right, r minus 1 right here, that was y. And let's draw a right triangle. Of course, Pythagorean Theorem, right? Now the hypotenuse is the radius. So let's go ahead and move this over here. Apply the Pythagorean Theorem. R squared equals r minus 1 squared. I guess that doesn't look like a minus there when I wrote it in that way, but plus 3 squared, which is, of course, 9. All right, r minus 1 squared. Okay, that's going to be r squared minus 2r plus 1. Plus 10, plus 9, because, yeah, it's going to be 10 when we add them. Let's go ahead and clean this up. Subtract r squared from both sides. Yep. And let's go ahead and add 2r to both sides. So 2r equals 10. Divide by 2, and we get r is equal to just 5. So we know that that little segment right there, that little part, is 3. We know that this is 5. So now we know that capital R, the radius of the large circle, is going to be 3 plus 5, which of course is 8. So we know that 2r squared, so double of the radius squared, is going to be the area. So 2r, right? 16 squared, 256. The area of square ABCD 256. Pretty cool. Let's see another method. All right, now the property we're going to use here is something that came out of a previous problem we did, where we had this perpendicular chord that was perpendicular to these two semicircles, this tangent, to these two semicircles, and we found out that the area of the diameter's parts, right, if you multiplied this times that, it equals the segment or the chord squared, like this right here. It's harder to say than it is to see. Anyway, we have that situation going on here. The thing is, you don't really need the circles. They don't really matter. The two sums of the two sums that make that diameter, if you multiply those together, that's the same as this chord squared. So, like this right here, and like that right there. If I take those and make an area and multiply them together, that's the same as that distance squared. And if you'd like to see the derivation of that proof, or the proof of that, or the derivation of that, I'll put a link in the description. So here's what we got. We make an area out of this. Yep. Area out of the red, and they are exactly the same. So we're going to apply that to our situation right here. Okay. So we know this is R. Yep. And we're going to call that little distance right there x. So we know that r would be equal to 6 plus x. Okay. Now, we also know that this is r. Okay, so let's call this little horizontal side y. So we also now know that r is equal to 4 plus y. Right? This is also r. Okay, so we know that x times r equals y squared. There's our third equation. So, pretty cool right there. Let's go ahead and solve these things up here, and then we're going to substitute, right? So we solve for x, we're going to solve for y, and then we're going to take those two values and substitute them right here for x and right here for y, get a single equation with r as the variable, and boom, there we go. So I went ahead and put the original equations up here so we could see how we substituted, right? We solved for x, solved for y, plugged those in right here for x and right here for y, and that's what we got. So we're going to distribute, and we're going to combine like terms and all that kind of happy stuff. So r squared minus 6r, and then r minus 4 squared. Well, that's r minus 4 times r minus 4. So that's r squared, and then minus 8r, and then plus 16, right? Cool. Now let's go ahead and simplify this, see if we can solve for r. If we subtract r squared from both sides, those things just go away. We can now add 8r to negative 6r, so we get 2r equals 16. And, of course, divide by 2, r is equal to 8. Since 2r is what we're looking for anyway, that's 16, we square that. 256 is the area. Hey, I hope you had a good time with this video. I hope you liked it. Hope you enjoyed it, got something good out of it. If you did, give me a thumbs up, maybe like, subscribe, share, all that kind of cool stuff. Check out my website, onteachingmath.org. I got all kinds of cool stuff in there. I will put a link in my blog to this PowerPoint that I made this video from. So if you're a teacher and you'd like to use it in your classroom, you can. It'll be there for you for free. And until next time, I hope you guys have a great day.